All right, welcome everybody. Paula, as usual, I hand it over to you to announce the speaker.
Thanks, Dirk. So welcome. I'm very happy that today's speaker is Tim Maudlin. Tim Maudlin is from the US, from the NYU, New York University, and he's also the founder of the John Bell Institute for the Foundations of Physics. So he's a professor for the philosophy of physics mainly, where he's very well known also due to his books on space and time and quantum theory. And as I just recently learned, he also teaches at Lugano, at the USI. So thanks for being here. It's a pleasure to have you. Tim Maudlin will speak today about the fundamental dynamics for quantum theory, and especially about the question why complex numbers appear. And I heard that you may ask questions in between if you want to clarify something. And otherwise, more general questions, please keep it to the end. Okay, let's go ahead.
Thanks, Paula. Yeah, so as I say, usually I prefer if I say something you don't follow, just ask me at the time. This is a kind of funny talk. I hope, if nothing else, there's a bunch of history that people don't know for the simple reason that I didn't know it until quite recently. And so some of the things I found I found quite intriguing. So let me just start with the motivational part, assuming I can get my thing to go. Let's see. Why can't I change there we go. All right, so there's a main question of how you go about discovering or inventing or coming up with new theories in a way that makes them seem at least prima facie plausible. And Newton thought a lot about this, and I want to just start with what Newton did. Because maybe I should say, this is in contrast to this very cartoonish view, sometimes called hypothetico-deductivism, where you say, well, somebody comes up with a theory, it doesn't matter how, right? Maybe it comes to them in a dream, who cares? And once you have the theory on the table, then you deduce consequences from it. Hopefully you deduce empirical consequences, and then you can go and test it, blah, blah, blah. But the idea that there's anything to be said about how the theory came about in the first place gets just pushed off screen. That's just bad methodological advice. And so you want to ask yourself, if someone comes up with a theory, well, how did you get there, right? What motivated you to do things this way rather than that way? Now, Newton used a word which these days, given the way it's used in logic, we immediately reject. And he said he wanted to deduce his theory from the phenomena. And he can't have meant and didn't mean what we mean by logically deduce. That is, that it follows of necessity from the phenomena what the theory is. So, and of course, he was under no illusions on that regard either. He didn't think he had an infallible sort of derivation. But nonetheless, if you read the Principia, he did motivate a tremendous amount of his theory starting with phenomena, right? Starting with data or observations. And he eventually gets to, right? When you ask him, why do you believe that there's a universal inverse square force law of gravitation? It's not, well, it came to me in a dream, right? I mean, there are very definite considered steps that get him there. Now, the whole theory isn't like that. If you ask, for example, where did the three laws of motion come from? There's no similar backing for that. But there is a very important part of the theory, which is to say, let's begin with some phenomena and see what we get. And I think that's a very powerful and useful kind of heuristics. So now in this slide, I'm just saying what I just said. He starts with data or observations of some phenomena, and then from those, he tries to get to certain features of the theory that he's going to introduce to explain them. So of course, in the case of quantum theory, we're in this very strange situation where we have a formalism that just kind of exists in mathematical space, and then all kinds of questions about how to understand it, about what, if anything, it's telling us about the exact nature of the physical world, and so on. And sometimes features of that formalism themselves have struck people as extremely strange. And so you ask, well, what was the justification for doing this? Now, you might say, well, the justification was just that classical physics had broken down. It was incapable of accounting for certain things. It was incapable of accounting for, say, black body spectrum or the photoelectric effect or the stability of matter or something like that. And then just by fiddling around, people came up with wave mechanics or matrix mechanics or whatever, and then you have a lot of just mathematical construction from there. But if that's all you have to say, then you can still be left with questions about why this or that mathematical feature shows up in this construction. So here's a question that's occurred to lots of people, which is that quantum theory from the beginning seemed to ineliminably or fundamentally involve complex numbers. And the question arises, well, why is that? Where is that particular feature coming from? Or the other way around, what does it indicate about the right way to understand this theory? Famously, this question was raised by Wigner in a paper the title of the paper is clearly much, much, much better known than the actual paper itself. It's a nice title, right? The title raises a nice question about the unreasonable effectiveness of mathematics in the natural sciences. And you sort of see this dialectic being set up saying, well, there are certain mathematical structures which you understand why mathematicians introduce them for purely mathematical purposes. Gee, I'd like to have a number that squares to -1. Okay, fine, I'll make one up and explain how it works. But if you ask, yeah, but then why would I expect that particular structure to play any fundamental role in physical theory? Some parts of math, the connection to the physical world seems more manifest, and other parts it seems quite remote. And the use of complex numbers was one that seemed quite remote to Wigner. So here's a quote from Wigner's paper. I'll just read it, if you haven't read it or if you haven't read it for a long time, because it's nice and clear. Let us not forget that the Hilbert space of quantum mechanics is the complex Hilbert space with a Hermitian scalar product. Surely, to the unpreoccupied mind, complex numbers are far from natural or simple, and they cannot be suggested by physical observations, right? So this is like, if you think of this Newtonian heuristic, look at the phenomena to motivate the theory, Wigner's sort of saying, well, no phenomena could possibly suggest complex numbers. Furthermore, the use of complex numbers is in this case not a calculational trick of applied mathematics, but comes close to being a necessity in the formulation of the laws of quantum mechanics. Finally, it now begins to appear that not only complex numbers, but also analytic functions are destined to play a role in the formulation of quantum theory. I'm referring to the rapidly developing theory of dispersion relations, right? So Wigner himself was puzzled and thought anybody who stepped back a second ought to be puzzled about why complex numbers are showing up in the foundations of this theory. There's another interesting fact, which is that when you look at the fundamental equation of quantum theory, I'm now talking about Schrodinger's equation. If you've been trained in classical physics, you're going to say, I know that, I kind of know that equation, but I know it as the diffusion equation, the heat equation. Except there's now this change, right? And this was something that Schrodinger himself, in his original set of papers, realized and pointed out. So Schrodinger wrote this, I don't know, 4-part paper or 4 collected papers. I'm not sure how to describe it. And when he begins developing the wave mechanics, he insists that he's going to use this psi function, and he insists that it be real. And in terms of a completely real psi function, he does problems that involve time-independent solutions, right? Time-independent wave equation. And it's only when he gets to the very last part, the 4th part of the paper, when he's now dealing with time-dependent perturbation theory, that he introduces a complex valued psi function. And not only that, he was pretty upset about it, okay? He wasn't happy. And so I'm just going to read the way Yammer describes the historical situation. I know that Yammer is not maybe the most reliable person, but he's not bad. And anyway, if you don't know this history, I think this sets something up rather nicely. So here's what Yammer has to say. In the 4th communication, the last part of the paper, Schrodinger developed his theory of time-dependent perturbations, realizing that in his equation 5.77, the eigenvalue E varies in passing from one stationary state to another, and consequently must not occur in the, quote, real wave equation, the Eigenwellensgleichung, which is to determine the spatiotemporal behavior of the wave function, right, as a function of x, y, z, and t. Schrodinger eliminated E, right? He can't use E because it's not a constant anymore, by means of this equation, psi equals little psi of q, e to the 2 pi I, notice the I, E over h t, and obtained the equation we all know and love, right? Basically, the Schrodinger equation. And you notice the I has appeared, right? The imaginary part has appeared. You're now dealing with complex numbers. Schrodinger postulated the validity of equation 5.84 that I just showed you, later called the Schrodinger time-dependent wave equation, also for time-dependent potential functions U. So you're also varying U. Recognizing that 5.84 has the structure of a diffusion equation with an imaginary diffusion coefficient. Now, you kind of look at that and you say, all right, I've now come up with an equation. I think I know that equation. I know it because I studied diffusion. But I've made this change from a real to an imaginary coefficient, right? And you might think, that's a curious thing to do, isn't it? Schrodinger relaxed his original requirement concerning the reality of psi. Again, for the first 3 sections, psi is supposed to be a real function, and admitted complex valued functions for what he called the mechanical field scalar psi. As an application of the time-dependent wave equation, he studied the phenomena of dispersion, which he treated as a problem involving a periodically varying perturbing potential energy function U. And so, this again ought to just, for anybody, and especially at the time, ought to seem a very strange thing to do. I mean, you can do it, right? Mathematically, there's no problem just plucking out a real number and sticking in an imaginary number. But from a physical point of view, you ought to be puzzled about what in the world, right? Why should that work? What is it about nature that's making this thing give me good numbers? And especially if you're in your mind, you're thinking, all right, I'm just dealing with a diffusion equation, but with an imaginary coefficient. Because you think, well, diffusion behavior and heat behavior, I know how that works, right? I mean, diffusion and heat tend toward equilibrium where everything has flattened out, right? I mean, thermal equilibrium is where the temperature is just constant everywhere. And diffusion, things diffuse again until you have kind of a constant density everywhere, and then you hit equilibrium, and that's the end of that. So why am I looking at a diffusion equation in the first place, and why am I now employing complex numbers, and why have I put in an imaginary coefficient? And so what I want to do in this talk is walk through a different approach, certainly not the one that Schrodinger took to get to his equation, and start with some phenomena and think about those phenomena, motivate a certain way of approaching the theory I'm going to construct from that, and try and get to a different way of understanding why we're dealing with complex numbers and some other features of the Schrodinger equation. So that's the scheme. All right. Now, before I start, let me again, this is all stuff I didn't know. Schrodinger was not a happy camper, right? When he did this, it's not like he said, "Oh, good, I have an equation that works, done," right? So here's actually what Schrodinger says, and this is the last paragraph of this fourth section of this paper where he introduces the wave mechanics. So again, I'll just read this because my guess is you're unfamiliar with it simply on the basis of the fact that I was unfamiliar with it. Some of it's hidden now because of my thing, but I'll try and make up the hidden words. Meantime, there's no doubt a certain crudeness in the use of a complex wave function. If it were unavoidable in principle and not merely a facilitation of the calculation, this would mean in principle two functions, which must be used together in order to obtain information about the state of the system. This somewhat unacceptable inference, I'm not sure, I don't know what that word is, so I can't say, believe of a very much more, admits of, I believe, of the very much more congenial interpretation that the state of the system is given by a real function and its time derivative, right? That is a second order equation. So the initial conditions are going to be both the value of psi and of the first time derivative of psi on the model of Newtonian mechanics, right? Our inability to give more accurate information about this is intimately connected with the fact that in the pair of equations for double prime, we have before us only a substitute, extraordinarily convenient for calculation to be sure, for a real wave equation of probably fourth order. Now, this is, two time derivatives and two spatial derivatives is probably what he meant by fourth order. When I first read that, I thought fourth order in time, man, that's really going out on a limb. But anyway, which, however, I have not succeeded in forming for the non-conservative case, right? So Schrodinger was really, really, really not happy about this. And he did not want to be stuck with a complex valued psi. And he was willing to go to pretty extreme lengths to get rid of it. And so just historically, that's a very interesting situation. So here's just, we have, that was all the setup. So we have now two formal features of the Schrodinger equation that prima facie, again, to the unpreoccupied mind, are kind of surprising. One is that it contains the equation itself. The Schrodinger equation contains I, and it describes the dynamics of a complex function psi. That's a little surprising. It's the equation itself is first order in time. It's not a second order equation like F equals ma. And the analogy, the closest classical analogy was to the diffusion equation with an imaginary coefficient. And that's weird, both because of the imaginary coefficient part and the diffusion part. Neither of those really looks like what you'd be expecting. So, question. Can we actually motivate or explain these very features in a way closer to what Newton did? Start with some phenomena, think about how you might account for those phenomena, and find your way to a theory that has this basic mathematical form. Now, we've got various dynamical equations that float around in classical physics and are used for various purposes. So let's just remind ourselves about the kinds of equations that already would have been in the air and available as models at the time that Schrodinger was doing this. Because we say, well, I'm going to motivate or somehow explain the structure of a dynamical equation one way because I've used similar dynamical equations to treat situations that in some way seem relevantly similar. So let's just look at some of the other equations that are just hanging around. So obviously we have F equals ma written here as in terms of the second time derivative of the position of the particles for particles, right? So particle equation. Or we could rewrite it as a pair of first order equations. This will be relevant soon. You say, well, no, the fundamental equation is actually F equals dp dt. And then if you ask what P is, oh, P is m dq dt, assuming m is constant. If m isn't constant, okay, then you have other kind of things. Now, how do we think about this? Well, in a way, I think we're going the opposite direction. I mean, what Schrodinger wanted to do was go back the other direction. So the first formulation is one that's second order in time. And the second formulation is a pair of things that are first order in time. In a way, what Schrodinger wanted goes the other direction. He said, well, I seem to have something first order in time. I want to get rid of the imaginary part and go back to something that's second order in time, so that my initial conditions are both the value and the first derivative of my field. Okay. So you can take this and write it in two different ways, as a single second order equation or a pair of linked first order equations. Well, of course, nobody was mentioning Newtonian mechanics here. The thing that was mentioned was the heat equation or the diffusion equation with constant coefficients. So we have this equation for some field U that it changes in time as some constant times the Laplacian. That's that equation. Again, if you just think about the way it works, the Laplacian is measuring how the value at a certain point differs from the immediately surrounding set of values of my field. And so by choosing alpha the right way, I get a dynamics where if the value of the field is high, it's going to be driven down. And if it's relatively low, it's going to be driven up. And so at the end of the day, this thing is going to evolve to a static distribution equilibrium where everything's the same. And if you look at that equation, the heat equation, and you just compare it head to head against the Schrodinger equation, yeah, it does look similar, right? You've got, well, you've picked up the H bar, okay, you've picked up the I, but you have d psi dt is equal to, and again, you have now the Laplacian of psi, you have a bunch of, of constants, and also a function, the u of psi function. But sure, anybody could see there's a similarity there. Here's another equation that's floating around, the Navier-Stokes equation that arises in fluid dynamics in the case of an incompressible fluid at constant density. So there are lots of implementations of fluid mechanics. There are lots of, as it were, Navier-Stokes equations, depending upon whether the thing is compressible or not, and whether, various constraints you can put on it. But if we just throw up the incompressible one, again, we know that we have du dt, alpha Laplacian u, that part looks exactly the same. And then you pick up three more kind of complicated looking terms, including a term with the gravitational acceleration. Why am I throwing up the Navier-Stokes equation? Well, one thing we know is solutions to it do give us waves, right? They give us water waves. They give us, waves in a fluid, waves that can interfere both constructively and destructively. So that's an interesting equation to have in your mind. And at least the leading term of it looks again like our heat equation. Of course, all of this is real, nothing imaginary there. The other thing to notice about this equation is it's not supposed to be a fundamental equation, right? This is an emergent equation. The fundamental dynamics is Newtonian. And then you say, I've got a Newtonian fluid, right? And then you say, I furthermore have a Newtonian incompressible fluid, or maybe it's compressible or whatever. And I put some more constraints on it. And from the fundamental dynamics, which really should be Newtonian mechanics, I derive the Navier-Stokes equation as at least a good approximation. And we all know that this, for anything in the physical world, this is only an approximation. Physical liquids, water is not incompressible perfectly. There are no perfectly incompressible fluids. They're not really fluids in the sense of being continua. You get down small enough and they have a molecular atomic structure and so on. So this equation from the beginning is only understood as some kind of approximative equation that can give you a good guess or a good approximate description of any physical phenomenon. Finally, there's another set of physical equations everybody would have known who was trained in physics toward the end of the 19th century, which is the Maxwell equations. And in particular, I want to look at the Maxwell equations for the free electric and magnetic fields. So we'll just pull, well, there we go, right? So we, again, what form do these have? First order in time, you have one equation that tells you how E behaves as a function of B. You have another equation that says how B behaves as a function of E. They're very similar equations, except the minus sign, and of course the constants, which have something to do with the speed of light. So those are some kind of mathematical skeletons for equations, for dynamical equations that everybody is familiar with. I said the Newtonian heuristic is let's start with a phenomenon and try and get to equations, not by just, confabulating or going to sleep and dreaming, but by thinking about this phenomenon and what kinds of dynamics seems to be suggested by it. But now we want to do it for quantum theory. So we have to start with some phenomenon. Now we know historically the thing started with black body radiation. It started with the photoelectric effect. It started with the stability of matter, which was very hard to understand in terms of classical electromagnetic theory. We could try to begin with any of those phenomena. But in fact, I want to start somewhere else, very unhistorical place, but a phenomenon that now, very much later and in retrospect, is constantly used as illustrating fundamental features of quantum theory, right? So we're not following the actual history here, but we are going to start with a phenomenon, namely classic two-slit interference experiments for particles, single particles, electrons or whatever. Right? So this is what we all are familiar with, we all use. It's worthwhile noticing that until Davison and Germer, I mean, this was not the kind of phenomenon anybody was starting with. In fact, Davison and Germer only got to do, got the idea to do their experiment because the theory had already been developed. And then they could say, oh, look, where could we look for evidence of this kind of behavior? But we're going to go the other way now. So Bell makes this kind of famous comment in 6 Possible Worlds of Quantum Mechanics. And again, I'll just read it. The last unromantic picture that I will present is the pilot wave picture. It's due to de Broglie and Bohm. While the founding fathers agonized over the question particle or wave, de Broglie in 1925 proposed the obvious answer, particle and wave. Is it not clear from the smallness of the scintillation on the screen that we have to do with a particle? And is it not clear from the diffraction and interference patterns that the motion of the particle is directed by a wave? And notice again what Bell's doing. He's saying, here's a phenomenon, go into the lab, right? Do this experiment, go into the lab. You'll notice these little dots. Those are suggestive of particles. You'll notice these patterns, these interference patterns. Those are suggestive of waves. Now, of course, when Bell makes this comment, in the context he's making it, he's really trying to promote the particle part of the pilot wave ontology, because it's the particle part that is radical and, bizarre, and who could possibly believe in particles? And the wave part, the Schrodinger equation part, that's everybody's, everybody believes in that. But I want to go the other direction here, right? I want to say, yeah, Bell's right. We have a phenomenon that just, you look at it and you say, that's a wave phenomenon, namely the interference bands. And so I want some kind of theory that will give me wave behavior. And then there are a bunch of things to notice. One is, of course, that this kind of interference phenomena already is familiar from light. And we have two-slit interference just for light, and we have interference bands just for light. The next thing to notice is that if you want to start with a phenomenon and try and motivate a fundamental theory out of it, you really want your phenomenon to be very simple physically. You want it to have as few physical parts to it as possible, because the more complicated it is, the more difficult it is to see the way through the phenomenon down to the basic dynamics, right? And so, I mean, that's why planetary phenomena were so great for Newton, because essentially the only force is gravity. That's it. There's no drag. There's no other kinds of things to deal with within epsilon. So observable facts about planetary motions are very, very, very directly reflective of the fundamental dynamics. And so you want phenomena that involve as little as possible. And in particular, the interference phenomena for both light and for these electrons or whatever in quantum theory appear to take place in a vacuum, right? You can do the experiment in a situation where, as far as you know, there's no medium. And if you say there's no medium, then you don't have to worry about what is the mechanics of the medium, right? The wave behavior is being developed quite directly out of the fundamental dynamics. Contrast this with the Navier-Stokes equation, which, as I said, really the idea is the fundamental dynamics is Newtonian mechanics. And it's only because of the medium and this very, structure of the medium that you get this wave behavior. Okay. Well, classic two-slit interference from a experimental point of view, do it in a vacuum. That's fine. It's still there. And so that suggests that something like wave dynamics really has to be built in at the fundamental level, at the level of the fundamental dynamics. It's not emergent the way water waves are emergent in continuum mechanics, right? There's nothing wavy about the fundamental dynamical equations of Newtonian mechanics. And you only get wave-like behavior if you decide, oh, I'm going to couple something, to a Hooke's law spring, or I'm going to couple a bunch of Hooke's law springs to each other, or I'm going to make some kind of elastic drum head that's going to wave up and down. All of that's fundamentally governed by Newtonian mechanics, but because you've set up these very special systems, you end up getting them described by wave equations. No, this seems to be something very fundamental. Good. So, unlike Bell, I don't want to focus on the particle part here. I want to focus on the wave part. And I want to say, all right, we want something in our theory where a fundamental part of the ontology, whose fundamental dynamics produces wave-like behavior, in particular produces both constructive and destructive interference, because that's what's characteristic of the phenomenon. Well, what are we gonna use here, right? What have we got that looks like it'll do the job? Now I'm just repeating what I said. You can say, well, I can get waves in Newtonian mechanics, but you only do it by building a certain kind of elastic medium that has very special properties. And that wave mechanics, of course, breaks down. I mean, the Navier-Stokes equations breaks down for actual water waves. thing, waves crash and the whole thing, it's not continuous anyway. We don't want to do that. All right. So I'm just repeating what I said here. I don't want to go via the Navier-Stokes equation, for God's sake. And the Navier-Stokes equation, again, has all of these 4 pieces, and you've got to have gravity, and you have all kinds of other stuff about how much friction there is essentially in this medium. Is it compressible or not? And so on. So if you look at that equation, you want to say, yeah, I can get wave behavior out of that, but that is not a promising route to where we want to go. Well, I can get simpler Newtonian waves out of simpler Newtonian systems. Again, if I've got coupled Hooke's law systems, I build a thing where the potential is a harmonic potential, and so on. But again, you first of all don't expect that a rigorous treatment of those will actually yield a simple linear wave equation, right? You expect the actual equation, the physically realistic one, will not be simple and linear, right? It'll break down. It might have a good linear approximation in certain regimes, but no. And well, what about the fundamental equation of Newtonian mechanics, F equals ma? That doesn't, you look at it, that just doesn't yield anything like wave phenomena on its own. So that doesn't look very promising. What about the heat equation? Well, I've already said this. You've got the heat equation. First of all, it's not supposed to be a fundamental equation. It's supposed to be a statistical result of the statistical averaging of a bunch of kind of randomly interacting things that are, their fundamental dynamics is Newtonian. Okay, you'll get diffusion and you'll get this tendency toward equilibrium. But again, that doesn't even help us, because the wavy phenomena with the interference effects, that's because we replaced the real coefficient with an imaginary coefficient, and then we had no idea physically, why am I doing that? So, you're again very puzzled. So what are we left with? Well, we're left with the obvious thing, electromagnetic waves, right? Electromagnetic waves are a really good match here. They take place in a vacuum, as far as anybody could tell, right? Except for the people who were holding on to Newtonian mechanics no matter what. So they said, well, if there are waves, I need a medium, and now I need a mechanical, picture of the medium, and I've got all these pulleys and these springs and God knows what, which never worked anyway. So the right thing to do there was to give up on the Newtonian picture, that this had to be there had to be a mechanical medium with stresses and strains in it. Just accept that I have a new kind of physical entity here, a field, or I have 2 fields, an electric and magnetic field. Take those as fundamental. They are not states of something else. And give me the equations of how those behave, the fundamental equations. And now we're back again to, in the free case, these are some pretty nice, clean, simple, beautiful, linear equations. And question, what is the fundamental character of these equations? They have the features we want. They seem to can describe some physical fundamental objects and how they behave without the interference of anything else. They can give rise to wave behavior. They can give rise to interference, both constructive and destructive interference. What's the character? What's the mathematical character that allows them to do that? So there are equations, and the first thing to notice is, as I've already mentioned, they're first order in time. You're only taking first derivatives, not second derivatives, which means I don't have velocities as initial conditions, right? My initial conditions are just at a certain time, what is the value of the B field everywhere? What is the value of the E field everywhere? The second thing to notice is the way they're linked to one another, right? That is, the change in E is purely a function of B, and the change in B is purely a function of E. Neither, as it were, affects itself, right? The immediate time change of neither field is determined by the value of that field. The change is determined by the value of the other field. You also notice that these things are linear. Obviously, if you double the values of the E and B fields, you have one equation. Scale them up, you'll have another equation because everything's going to be nice and linear. That's something else we want. And you'll notice in this case, you have this kind of very beautiful symmetry if you just ignore, I mean, I've dropped out the constant, which, as you know, can, as it were, be set to 1. The equations look, almost exactly the same except the negative sign, which is an interesting observation, and one that will play a role in what we're going to do. So let's just give a name to these kinds of equations, which, all right, I made up a name: reciprocal first order dynamics, RFD. Reciprocal because the change in E is just a function of B, the change in B is just a function of E. First order because they're first order, right? So you've got a pair of reciprocal first order equations for fields. And these give rise, as we know, the solutions to these equations include the wave solutions that we're all familiar with: linearly propagating wave solutions, infinite plane waves, linear and circular polarizations, right? Think of the entire nice set of solutions to these equations. And because it's all linear, once we have a basis, say in terms of plane wave solutions, I can then get every solution by a linear combination of those. That's very convenient. That allows me to bring in Fourier analysis and do a bunch of very fancy things and convenient things for finding solutions. And so I would say, if you want to say, I want a fundamental dynamics that gives me wave behavior, that gives me linear behavior, and so on, let's start here. Let's start with reciprocal first order dynamics. Now, I'm going to give you a little bit of history, which I find interesting. And I didn't know anything about this. So again, I'm assuming this is not well known. This is just a little break in the narrative for your amusement, which is that way before even Maxwell's equations arose, there was already this realization that, and it's kind of, you can think of it as this particle wave duality thing coming up much earlier. There was already this realization in the early 19th century that they had a good theory of particles, at least gravity for particles, and they had other theories or principles, mathematical principles for optics, for light, right? But if you kind of think about them, they didn't seem to have anything to do with each other, right? The mechanical theory, the Newtonian gravitational theory, and that was really the only proper Newtonian theory there was, just didn't seem to have anything much in common with optics at all. And so you wonder, well, gosh, there must be some single physics here. I mean, there must be some fundamental physical principles that are allowing to produce both optical phenomena and particle gravitational phenomena. Newton himself, of course, wanted a corpuscular theory of light. So he would have thought ultimately optics was to be understood in terms of something like his own mechanics. But he never got that to work out. And everybody knows if you kind of try to do that in the straightforward way just to get Snell's law, you find that you're going to have to say that light's going faster in water, say, or in glass than slower, right? Things get speeded up rather than slowed down. That didn't seem to work out very well. Now, Hamilton, this is what I didn't know anything about. It's really nice. 1933. So this is, 1833. This is 2 years before what we call Hamiltonian mechanics. Writes this very nice paper, right, on a general method of expressing the paths of light and of the planets by the coefficients of a characteristic function, right? So you see, it's this mechanico-optical unification, right? A general method that will tell me both how do planets move, which is what we would say, all right, that's Newtonian gravitational theory, and how does light move, optical theory. And Hamilton is interested in kind of finding a common general method, right? A common math for this. And he starts out by saying, well, on the optical side, some of that stuff is predicted by some extremization principles, right? Least time principles or least action principles. This was already known. Although he then, if you read the paper, it's very nice because he says, but that's not, can't be the general principle, because sometimes I can set up an optical situation where instead of the least time, it's the greatest time. Or sometimes it's neither the least time nor the greatest time, but nonetheless, you have a stationarity, right? It's stationary under small perturbations. So he says, I don't really want a least action principle or a least time principle or a greatest action principle or a greatest time principle. I want a stationary action or a stationary something principle. And that can give me both reflection of light and refraction of light correctly, right? I can get Snell's law, stuff like that. Now, he was aware of, so he starts with the Lagrangian quantity that had been associated with the least action principles, and he replaces the minimization principle with the stationarity of action principle, and he, replaces the Lagrange function with the Hamiltonian function, which we can think of loosely as giving the difference between kinetic and potential energy. And we know that in that kind of very generic mathematical structure, you can set things up to get Newtonian mechanics out, and especially Newtonian gravitational theory out. But now he's saying that very same mathematical structure I can set up and get optical phenomena out as well. So I seem to have now this general approach. And so what is the form of it? Well, we all know we end up with these equations. dq dt is the partial of this function h with respect to p. dp dt is the negative of the partial of this same function with respect to q. And already, okay, you're going to look at that and say, hey, that sort of looks like reciprocal first order dynamics, right? We need to add a little bit to really get what I called reciprocal first order dynamics. We need to add, suppose the h function is the sum of two parts, one of which is expressed entirely in terms of q, and the other is expressed entirely in terms of p. Then when I take these partials, I'm going to end up saying that the way q changes is just a function of p, and the way that p changes is just a function of q. And then I really have what I called reciprocal first order dynamics. The exact form it takes will depend on what these partial derivatives of h look like. But we could just say in the case where I can split the Hamiltonian into these two parts, so I don't have any PQ terms, just programmatically, then we've got that dq dt is some function fp of p, and dp dt is some function fq of q, put in the minus sign. And then you can, well, gee, that there now does again look like reciprocal first order dynamics. And I can ask questions like, this function f of p, is that a linear function of p or not? Is f of q a linear function of q or not? And if they are, you can start to have expectations. And if these are for fields, you can start to have expectations about the kinds of phenomena you might get out of this thing. So let's just do the direct equation with Maxwell's equations. If I just take my two equations and line them up this way, you're going to say, yeah, those look pretty similar. It's just that in the case of Maxwell's equations, the function f of p and the function f of q are pretty much exactly the same function. Namely the curl. What does that mean? Well, it's nice for the Maxwell equations that they're the same function, because that means there's a very, very easy way mathematically to bundle this pair of equations into a single equation. All I need is a bookkeeping device that'll keep track of the E field and the B field separately. And there's an obvious such bookkeeping device. Instead of a pair of real fields, I'm going to create a single complex field. I'm going to let E be the real part of that and B be the imaginary part. And now I have a single field, a single complex field, define it that way. And then you say, well, how did I get into this business? The answer is it's a bookkeeping device, right? That's why I'm using it. I need to somehow separate. I've got two different fields floating around. I want to keep track of which is which. I want to have just one equation, okay? And because in the reciprocal first order dynamics, the change in B is a function of E and the change of E is a function of B, it means that equation, that single equation must contain an I, because it's the I in the fundamental dynamical equation that's telling you that the change in this field is a function of the other field, right? So the reciprocal nature of that pair of equations then leads you to expect I'm gonna have a single equation of a complex field, and that single equation will have an I in it. And if I just do it right now this is just plugging in. I've defined F as E plus IB. I'm now just going to plug that in, take its derivative in time, plug in Maxwell's equations, and run this through. And everybody here who knows their math better than I do says, oh yeah, this is what I'm going to end up with. I now from a pair of equations for a pair of real fields, I now have a single equation for a complex field, and I've picked up a 1 over I in that equation. Okay. All of this coming out of just thinking about electromagnetism. Now, here's some stuff I found out from Michael Kiesling. So if it's true, praise Michael. If it's wrong, throw rocks at Michael. This is what he told me. It seems right. This is an obvious idea, right? This is not a subtle idea. And in fact, it occurred to people. And apparently, historically, about the first person it occurred to write down was this guy, Heinrich Weber. First I ever heard of him. Interesting place he wrote it down. The 4th edition of Riemann's Partial Differential Equations of Mathematical Physics. So this book was a report based on these lectures that Riemann gave in 1854 to 5, and then again in 1860 to 61. So this is before Maxwell's equations even existed, right? Riemann's just giving mathematical equations for dealing with Newtonian mechanics. And they're such a success that they keep reissuing editions of these lecture notes, essentially. And each editor of each succeeding edition then adds their own things to it, right? Which have nothing to do with Riemann. Riemann didn't do this stuff. So by the time you get to the 4th edition, they give it to this guy Weber, and he decides to put in this way of re-expressing Maxwell's equations in terms of a single complex field, right? So this idea of why am I using complex numbers? Well, because essentially I'm dealing with reciprocal first order dynamics. You could trace back, I would say, to Weber in 1901. And then by the principle that nothing is ever named after the person who did it, this complex vector apparently is now called the Riemann-Silberstein vector. Riemann had no idea about any of this stuff. And I guess Silberstein rediscovered this some years later. That's my understanding of the history. So if you know, ask Michael about it. And then, okay, now we have this equation, one equation of a complex field. It's a first order equation in time. It picks up the 1 over I. That's a way to do Maxwellian electrodynamics, free Maxwellian electrodynamics. And you say, well, why am I using I all of a sudden? And now we've told a whole story about why you're using I. Okay. The explanation is through this chain of thought. Easy way to get linear wave dynamics into a physical theory is via reciprocal first order dynamics. as exemplified by free Maxwellian theory. If the equations relating the value of one field at a time to the time derivative of the other at the time have the same basic form, you can bundle them together into one equation, and the 1 over I has to appear in the dynamics because each field is controlling the dynamics of the other one. And then, of course, we have Schrodinger's equation, which then you see that's basically the same idea. It's not quite as simple because it's not just the curl of this complex field. And in fact, you have now the Hamiltonian operator, which does divide into two pieces, a p-dependent piece and a q-dependent piece. And then by taking partials, you can actually make those two pieces look quite different from each other, whereas in the case of Maxwell, it's just the curl, it's the same. Okay. And so we have now the basic, this basic operator in Schrodinger's equation is playing the role of the curl, only I'm taking essentially partial derivatives of it. And that way I have a kinetic energy term, which is just a function of P, and a potential energy term that's just a function of Q. And the minus sign, of course, you'll remember already, even in Maxwell's equations, we had curl in the one case and minus curl in the other. And all of this is going to be connected to symplectic manifolds and blah, blah, blah. Okay. We're not bringing in particles. We're not bringing in the Lorentz force. If you had a term in the Hamiltonian that's a function of both P and Q together, if you were a P times Q term, then this wouldn't work so well. And of course, we also know if you have a P times Q term in a classical theory, then you don't know what to do when you come to quantize it because you put the hats on and it depends on the order you write them in, blah, blah. Okay. But if this operator, this fundamental operator, here now the Hamiltonian operator is linear, then we're going to get a linear kind of dynamics. So that's really the feature we're looking for. Good. Now, that's the basic story about why am I dealing with a complex field, and why do I have this particular kind of first order dynamical equation that includes 1 over I in it. Now, I just want to make another point about this, which is this is, as it were, the right story. If this is giving us physical insight, it also tells us a bunch of obvious things about time, what we call time reversal symmetry. So I'll finish this. I'm almost done. But probably half of you can see how this goes already, but I'll just do it slowly. So, you have this formal feature of the Schrodinger equation, which is that it has what's called time reversal symmetry. Now, I complain about this all the time. One of the many things I complain about. Time reversal symmetry sounds odd because what the hell do you mean reverse time? Okay, if you do an experiment in a lab and you get a result, and you have on one wall of the lab a big mirror, and you say, well, why don't you do that same experiment, only reverse parity? Well, what do you mean reverse parity? Well, I'm going to take away that mirror and put in a pane of glass and now build a lab over on that side such that it looks just like the mirror reflection of this one, right? You know what to do, right? At least to some extent, you know what to do. I was using right-handed screws. I'll use left-handed screws. I have coils that go like this. Now I need coils that go like that. You sort of know what it means to do a parity reversed experiment and then ask, do I get the parity reversed outcome? But if somebody does an experiment in a lab and I say, now, can you please do that experiment again, but reverse to the direction of time? I think they'll be kind of puzzled about what it is you're requesting that they do, right? At a purely instrumental level, I don't really know how to turn time around and run it the other direction. So what usually is meant here? Well, in Newtonian physics, something quite definite is meant, but that's connected to Newtonian physics being fundamentally a second order dynamics, right? In Newtonian mechanics, you mean, well, reverse the momentum, or basically reverse the time derivatives of things, right? But essentially, if you think of Newtonian mechanics as being expressed in terms of P and Q, and P is itself a time derivative because it involves velocity, then when you say reverse time, what you really mean is reverse the time derivative, right? If the velocity of the particle in the first experiment is this, reverse it and have it do that, right? That makes sense. Notice that's a spatial reversal, right? Instead of doing this, you reverse it in space. Okay, so what happens in Newtonian dynamics? What does time reversal look like in it? All right, when we describe the entire system through a period of time, we've got two functions, Q of t and P of t. I started some initial time, Ti. I ended at some final time, Tf. And so I have the state of the system Q0, P0. It starts there. It follows the dynamics and ends up in some final state, QF, PF. And now what I want to do is take a second system. For its initial time, I'm going to use the final state of Q of my first system. And for its initial time, I'm going to use the reverse of the final state of P for the first system, right? I'm going to reverse the P and keep the Q the same. And then I'm going to map the times. Final time here goes into initial time here, and then they go in the other direction. So the initial time here maps into the final time there. And then you ask, okay, is that going to be a solution to the equations? Will that be a different new solution? So basically, what we're doing when we say we're reversing time, we're not reversing time at all. What we're doing is we're reversing P. We're reversing P of the final state. We're keeping the same Q of the final state. And then we see whether it retraces its steps as time goes forward. I can't reverse time. Does this new system, as it were, retrace the steps of the old system, especially with respect to the Q values? Do the Q values follow exactly the same pattern, but in the opposite order in time? But what do? Notice, we reverse one part of the system. We don't reverse the other part of the system. We now have a new state. We let that run forward and we see what happens. So, of course, in Maxwellian electrodynamics theory, that's also time reversal invariant, but that can't have anything to do with reverse the time derivatives. Why? It's a first order theory, right? The time derivatives don't matter. They don't come into they're not part of the initial conditions. So what do I do? Well, we all know what I do. I keep E the same and I reverse B. Now, there can be various kind of hand-wavy arguments about why I keep E the same and I reverse B. Again, reverse B kind of spatially, and it's spatial representation. But in fact, that's what I do, right? I take an initial state of an electromagnetic field, let it evolve to a final state. Now take the final state, reverse B, and let that evolve forward in time and see if I get the original initial state with B reversed, right? Now, you know, if you just look at the dynamics, it will be time reversible in that sense, right? It will work. Why? How would we now? You just say, and it's the answer is so obvious. How would I implement this so-called time reversal procedure operator if I use the complexified version of Maxwellian electrodynamics? Well, keep E the same, reverse B, i.e. take the complex conjugate, right? Complex conjugation is going to show up in a very expected way as the implementation of what we call time reversal in this kind of reciprocal first order dynamics. And if you sort of think through what formal features do the dynamics have to actually display what we call time reversal symmetry, it comes down to a pretty simple thing. Because what do we want? You sort of think we have a base object. In the case of Newtonian mechanics, this is the positions. And in the case of Maxwellian electrodynamics, it's the electric field. And we want the behavior of that base object to reverse in the sense of going through the very same set of states in the opposite time order, right? That's what will count as getting us a time reversal. Now, since it's the positions in Newtonian mechanics, that means, of course, if a bottle can fall off the table and smash on the floor, then a bunch of disconnected pieces of glass on the floor can, in principle, jump up onto the and assemble themselves into a bottle onto the table. Right? That's showing the movie in reverse, stuff like that. Right? That's what we want to have happen. Now, what mathematical characteristics does the fundamental dynamics have to do that? Well, we're going to keep the same Q. We're going to do something to the other part, to the P part or to the B part, so as to systematically reverse dq dt. We want dq dt to reverse. Well, here's a nice feature that could happen. I say make an assumption or notice this is true. Notice, what if the function f sub p of p, the function in terms of which the value of p gives me dq dt, is linear in p? It might be, it might not be. Suppose it is. Then we know what to do to reverse dq dt. Just reverse p, right? The linearity will carry that through. And so that does what we want. And then you can see, as long as that function is linear, the thing will, in fact, the Q part will, in fact, keep retracing its steps, right? Because dq dt will always will be retracing the steps. And so, and the P will always remain opposite to what it was if as long as the P change is also has the right form. And so what we want, and this is now just, I won't work through this. This is doing it in a discrete setting where instead of worrying about a continuum, I'm doing it in discrete steps. And that's because I'm interested in discrete space-time. But it's exactly what you'd expect. In discrete space-time, it's kind of what you expect up to epsilon. There's a tiny little difference, and that epsilon goes to 0 in a continuum. But that's what's going to give us time reversal if the fundamental dynamical equation has this linearity in it. And if I express my pair of fields, fundamental fields, as a single complex field, then you see why time reversal will be implemented by complex conjugation. Okay, so now we're at the end. Wigner was puzzled about why there were complex numbers in quantum mechanics. Schrodinger was upset that there were complex, and he put them in, right? He was upset that there were complex fields in quantum mechanics. He wanted to get rid of them. And he was willing, more than willing, to go from a first order dynamics to a second order dynamics, more like Newtonian mechanics, in order to get rid of the complexity in the mathematics, right? But I claim this is all wrong-headed, right? The correct heuristic route to understanding why we have complex fields and why I occurs in the fundamental dynamical equation, namely Schrodinger's equation, and why time reversal is implemented by complex conjugation, all of these are answered by the same observation, which is that we want something like wave dynamics. We want something that will give us both constructive and destructive interference. The easiest way to get that is by reciprocal first-order dynamics. And if we have a reciprocal first-order dynamics with a linear dependence of the dq dt on P, then there's going to be a natural representation of that in terms of a single complex field, and time reversal will be implemented by complex conjugation. So, one last point. I've probably bored everybody today. I'm not too far off on the time. A last observation, and this is, again, I like to complain about things. This is a whole big new thing I'm going to be complaining about for the rest of my life, so you'll hear this over and over again. I think the pedagogy, I'm not sure what this point is. I forgot what my last slide is. Anyway, think about the way physics actually developed and the development away from Newtonian mechanics. I mean, this is my big bugbear now, is that when students learn physics, they learn it via Newtonian mechanics. We even teach them the math via Newtonian mechanics. They imbibe a whole bunch of principles of Newtonian mechanics into their fundamental picture of physics. And they still do. And they still use it. And they still even implicitly rely on it. And we know Newtonian mechanics is wrong. We know it's wrong. We know it's false. And it's not just false in some little way. It's fundamentally false. And I hope you've seen in this particular story, one of the features of Newtonian mechanics, namely that the fundamental dynamics is second order in time. That, if you stick to that, or if you have intuitions that are generated of that, they're not going to get you to the right place. Right? I mean, in my opinion, if we had to introduce a classical theory on this assumption that classical physics is easier to understand and a nice sandbox to learn some of the math, I would say teach them Maxwellian electrodynamics, right? Not Newtonian mechanics. Anyway, but let's think about how things went. How did we get to electric and magnetic fields? They were fundamentally new kinds of physical postulates. And a lot of the struggle in physics over the period of at least, a century was accepting that there could be things like electric and magnetic fields that were not mechanical states of a mechanical medium, right? Because that was the way to keep the whole thing Newtonian. But why did we do that? Well, there were some kind of obvious things we noticed happening. Motion of matter, the way charged particles behaved, the way iron filings behaved, and so on. We had these phenomena. We tried to look at those phenomena and say, what does that suggest? Well, lines of force. Well, we've got now these, we've got these things, unlike particles that only exist at one point, we have fields that are defined everywhere, and they have a dynamics and all of that. That was a big struggle. Why did we postulate them? We postulated them not because we directly observed them, but because we could see some stuff and its behavior suggested that field-like objects existed. In that sense, we made progress when we postulated E and B. Their role was that they are not directly observable, but they were, if you will, guiding fields for things like iron filings or charged particles. So if we take that same attitude and we say, all right, we need to postulate something new, it's going to be a field-like thing. Why? Because it's giving rise to obviously wave-like behavior. It's giving rise to interference phenomena, which the only real way we know how to get that mathematically is through wave equations. And it looks like this wave phenomena is very fundamental. It's not a matter of there being a medium. It's not a matter of a complexity in the system, but actually it appears in the most simple kind of systems we can create. Then we go through this reciprocal first order dynamics. Then we say, well, then I might as well just use a single complex field. And we're there, and we're there also under certain very simple assumptions with the time reversal features of it. So I think this would be a way to wean us off of Newtonian intuitions and Newtonian principles, which I think tend to get in our way when we try and think our way through what the deep lessons of quantum theory are. Okay, and I think that's the end. That is the end.
So thank you very much, Tim. And let me see.
A little bit louder because I have problems. Thank you.
Yeah, so people are clapping their hands in the
Well, it's dead silent here.
participants. I don't know if you can see it.
Let's
You
do
can
it properly, huh?
only see it. So I don't know. Should we make it such that we can see everybody, or should we keep the lecture?
Maybe if there's some questions
Yeah, maybe there's still some
But,
questions. So
for the
let's
lecture,
start with questions first.
Andy.
So
I think
Robert,
that's the first.
yes, first question. Please, Robert.
Okay, I'm just putting
All
my face on and opening up my voice. Nice talk, too. Very interesting. But I'm not sure that I understand the logic of what you've done. We start off with the problem of why do we have to use complex functions in quantum mechanics? Is that fair?
Well, I'm not sure have to is too strong here, right? Why would it be a natural thing to arise? I mean, you obviously you can do Maxwellian electrodynamics without ever introducing a complex field.
Well, that's exactly
Typically
my
not done,
point.
right? But that it can be done, and the kind of mathematical simplification that comes from doing it, at least compactification is very evident. So if you ask me, do we have to? No, the answer on this view isn't we don't have to, but we might very well find it convenient to do so. Does that
Okay, well, I take that the $1 million question has been, why do we have to use imaginary numbers in quantum mechanics, not why are we allowed to?
Well, then I'm not answering, then I don't get the $1 million.
No.
But
Okay,
I don't know why one
I'll
should
send
think
you
that's a
some
good thing.
papers on the $1 million question. But thanks.
Yeah, I mean, that's, yeah, let me actually say another word about this before. My fundamental orientation for years and years and years, and it's getting worse and worse and worse, so don't have hope for me, is we ought to be puzzled from the beginning about why we're using arithmetic or algebraic representations in physics. Because number fields have to have, for their definition, both an addition and a multiplication operator. And I don't think there's anything in nature that corresponds to multiplication. I think there is something in nature that corresponds to addition, right? So in geometry, if I have two line segments and I say add them up, you know what to do, right? You put them end to end, and now I have another line segment. But if you say now multiply them, I don't really know what to do. I mean, I can make a rectangle, but that's not a function that takes two line segments and returns a third line segment, right? That's a function that takes two line segments and refers an error and gives me back a different kind of quantity. And so I'm very suspicious of the part of the mathematical representation that relies on multiplication. And obviously, I thought of as the square root of -1, or one of the two square roots of -1. That's thinking about it entirely in terms of its multiplicative properties. So if someone has the idea, I want to know why I can't do physics without somehow bringing I into it, without it's a necessity. I don't think there's any such answer. I don't think there should be such an answer. I think that would be, as it were, wrong to propose that there's such a strong reason, because the very feature that makes an imaginary number imaginary is its multiplicative structure, and I don't think that has any physical significance.
Okay, well, I'll send you some articles that think otherwise, and then we can go from there.
I'm certainly not claiming this is an uncontroversial view.
Okay.
So I see that there are also some questions in the chat. So I think, should we just proceed like one from the chat, one from the audience?
Fine,
So in the chat, there's a question by Roshan Raj or Rai. You want to present the question, or should I read it? I don't know if Roshan is. I can read it maybe. So the question is, should we say, following this analogy of f equals e plus ib, should we then say true wave function equals particle attribute plus I star wave attribute?
No, I wouldn't think of it that way. I mean, the thing about, okay, Newtonian mechanics was really developed for particles. And the thing about particles is that a single particle has a definite position at every time and a definite velocity at every time, at least according to Newton. And then what you're looking for are equations that tell you how those positions and velocities will change. Whereas a field is always defined everywhere, right? You can't ask, where is the field a minute from now? Because the field is everywhere now, and it's everywhere a minute from now, and it's everywhere 2 minutes from now. So the point here is that wave behavior is fundamentally field behavior. In order to put together particles to give you anything wave-like, you need a whole lot of them, like in the ocean, and they need to be coupled and they need to interact in certain kinds of ways. So it's not that the two reciprocal parts of this, one is particles and one is fields. They're both field-like, just as the electric field and the magnetic field are both field-like objects in classical electromagnetic theory. Now, I could go on and on and on. I will just say a word. In the standard way that Maxwell's equations are presented, we first learn them using vector calculus. And in that, the electric field is a vector field and the magnetic field is a pseudo-vector field. So we kind of know they're different sorts of things. I think all of that is very misleading, and that really what's going on is the electric field is what I call a one field, and the magnetic field is what I call a two field. This will sound reminiscent of people to the theory of forms, of one forms and two forms. And it is sort of reminiscent, only I'm developing this in a context where I don't need to do any integration, so I don't need integral forms. But in any case, both E and B, whatever they are, have this field-like characteristic that they're always defined everywhere, unlike a particle, which is always only somewhere. So all of this is just about understanding the structure of Schrödinger's equation. The further question of how, if you think there are particles, as in the pilot wave theory, how the particles get into this, then we would have to get into the guidance equation in Bohmian mechanics. And that's not a piece I've considered here. And it's something I didn't want to get into because I think this story, everybody's got Schrödinger's equation. Everybody's got a complex field. Everybody's confronted with the question of, why am I dealing with a complex field? Everybody's confronted with the question of, why does Schrödinger's equation have the structure it has? And this is supposed to be an approach to that.
Okay, thank you. So next question is by Ward.
Hi, Tim. Thanks for the interesting talk. Maybe first as just a minor remark. So what you said about time reversal and all that resonates well with some work I did where I had this idea of accounting for complex conjugation in terms of the real part of the Schrödinger wave function. So if you want to have time reversal, if you want to have the time reversal transformation as just the reversal of the instantaneous states, and if you just take the real part of the wave function, that exactly does the job, because the imaginary part is related to the time derivative.
Yeah.
Okay. But so like on the level of a wave equation, if you take Schrödinger's equation, or you take just the wave equation for the real part of the wave function, which gives you this fourth order equation, the spatial derivatives, and so on the level of the wave equation, you could take either one of those. Okay, they would be equally difficult or easy. Okay, but I'm not sure exactly. But I thought, but maybe you can correct me. I thought Schrödinger's motivation was, if I look at the probability distribution, that's going to be really messy if I just phrase everything in terms of the real part. Because mod psi squared is going to have this mod squared of the real part, plus then some messy stuff involving inverse Hamiltonian operators on this real part and time derivatives. And well, was that the reason to give it up, or was there one reason?
You know, look, my knowledge of the history here is very thin. As I said, I learned all this stuff within the last few months. I don't have a deep understanding of it. I had heard before from Craig Callender about Schrodinger's desire to just use real fields and going to higher orders in order to achieve it. I mean, I read you the quote that's at the end, you know, it's literally the last paragraph of the paper where he introduces wave mechanics. He's very upset about it, them being complex, and is certainly willing, right, to add more in terms of the mathematical structure of the equation in order to get rid of the imaginary part. Now, let me just say a word to make my own position here even more clear. As I said, one of the other things that this talk has nothing to do with it at all. One of the things I've been working on is discretizing space and time. And what happens if you discretize things is that you just can't keep second order equations, because in a continuum, in a second order theory, your initial conditions are both the positions and the velocities. And in a continuum, you have an infinite number of velocities, right? You have this incredible variety of velocities you can attribute to items. In a discrete setting, like maybe there are 4. You know, any particle you could kind of attribute it a velocity, but there's a very, 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 very restricted set. And it's just not going to work well, right? So if you don't like continua, or if you're interested in investigating anyway, discrete space-time structures rather than continuous ones, second order equations, fundamental second order equations, are just kind of ruled out from the beginning. You really are looking for fundamental first order equations. So for me, this is very good news. You know, if Schrodinger says, I'm willing to go up to second order in order to do blah, I'm going to say, no, I don't want to do that. That's why I'm very happy about the Dirac equation, right? First order. These things, because these things I can understand in principle how to set them in a discrete space-time. Whereas if you gave me a fundamental second order equation in a continuum, it's just going to fall apart, I think.
But you would always be able to reformulate it in terms of first order in time equations, right?
I'm not sure. I mean, that way of translating into one or the other, we're most familiar with in a continuum setting. How
in a
discrete setting is something, I mean, first of all, there's no unique answer, because all kinds of discrete settings you can have. I'm really not sure that there's going to be an algorithmic way to do that in a discrete setting.
Okay, good. Thanks.
Okay, so let me take the next question from the chat. So Marcello Fonda, either you can also ask yourself, or otherwise I read it. Let's see. So he cannot speak loudly, so I read it. So he thanks you very much for the talk and says he really appreciated the ideas. And his question is the following. Decoupling the RFD for Maxwell equations yields 2 wave equations, second order in space and time, because of the curl, first order in space operator. Decoupling RFD for Schrödinger yields 2 equations, which are second order in time and fourth order in space, because the Laplacian is second order in space. Could you please expand on how we should interpret this equation?
Yeah, I mean, I could a bit. This is the same thing I was talking to Ward a second ago. The curl operator. All right, now there's a long story.
Okay.
The curl operator. Right, actually, let me say, I'm going to say a few words. I'm going to understand that people are going to go, what the hell are you talking about? Okay, but let me say the few words. As I said, if we start with electromagnetic theory, we've got E and B. Everybody agrees E is a vector field and B is a pseudo vector field. What exactly that means is not entirely clear the way you're originally presented to. You say, well, they behave differently under parity. Okay, but yeah, but okay, what's going on? My way of understanding this is that the E field is essentially a thing that's attributed to one-dimensional elements. Think of them as vectors, yeah? The B field is something that is fundamentally attributed not to that, but to areas, right? To two-dimensional elements. And so what the Maxwell's equations are telling you is that the value of the E field is controlling the change. The value of a field on the one-dimensional elements, is controlling the change on the two-dimensional elements, and the value of the field on the two-dimensional elements is controlling the change in the one-dimensional elements. So what shows up as the curl in both those equations, when I rewrite this in my terms, are two different operators called lift and drop. The lift operator takes you from a one-dimensional thing to a two-dimensional thing. The drop operator takes you from a two-dimensional thing to a one-dimensional thing, also from a one-dimensional thing to a zero-dimensional thing, right, to what we call a scalar field. So that the appearance of the curl in the standard Maxwell equations in both those places is misleading. It is an artifact of trying to use vector calculus, which basically only gives you two tools, scalar fields and vector fields, to deal with a physics where you've really got, as it were, scalar fields, vector fields, two fields, area fields, even three fields, fields that are associated with volume elements. And it turns out that in three-dimensional space, and only in three-dimensional space, are there correspondences that allow you to, as it were, use vector fields to represent things that aren't really vector fields, right? That we call pseudo-vector fields. And to use scalar fields to represent things that aren't really scalar fields, we call them pseudo-scalar fields. What you've really got are zero fields, one fields, two fields, and three fields. So when you do it all that way, I mean, I'm not sure about the decoupling, but again, for my reasons, I want to keep everything first order in time at a fundamental level. As soon as you make things second order in time at a fundamental level, then some of your initial values have to themselves be time derivatives, and it makes everything a mess. So, you know, there's a question of what you can do. There's a question of what you want to do. I have very definite reasons for wanting to keep things first order. And I could tell you a lot about why the standard presentation of Maxwellian electrodynamics in terms of curls and divergences and gradients is kind of funny and isn't quite right. And I could give you a whole new way to do it that looks much cleaner. That's another talk. I understand the kind of thought that Schrodinger was doing, right? He wanted to decouple these things. He wanted to get rid of he wanted to replace the complex field. But you just have to think through what were his motivations and what other motivations might you have. And I can, it's not that I need to run down his motivations, but I could give you a whole bunch of motivations for trying to do this the way that I presented here.
Okay, thank you. Let's keep on with Mario now. Mario? Hi.
Hello. Hi, Paula. Hey, Tim. Good to see you. I have a question on the ontology of the wave function once we take your presentation at face value. So given the analogy you made with the electromagnetic wave, so if we have a complex function or a complex wave, then we have these two parts, and then the two parts are actually, these are the physically meaningful things in the world. So if we look at the wave function, then we have a complex wave function. How should we think of the wave function? Are there two wave functions or two parts of the wave function that are the real thing? So we should not think as the wave function as one big complex field, but rather as two real fields. Is that the way? So I'm just interested in what you have to say about that.
Yeah, I mean, again, from my point of view, if you think about even the terminology you're using, is it a real field or a complex field? That at a physical level, that doesn't make any sense, right? Because the real and complex are references to the arithmetic structure that you're using to represent this thing, right? I don't think they're either real or complex numbers in nature. So as soon as you say, but I can say without you know, in a pretty physical way, I've got two fields, right? And their behavior, the behavior of each depends on the other in a certain specified way. Is that two real fields or one complex field? To me, this is not a sensible physical question. And once you see that that situation can be represented using both a pair of real fields and a single complex field, right? You say, well, I don't really see that's a decision that has to be made. Now, of course, you know, once we get up to psi, the other issue is psi is not defined on physical space anyway. So that's, you know, that's the whole non-locality bit to it. That's an entirely different issue. So this is sort of obviously there was nothing non-local in anything I did. I only represented some Maxwellian electrodynamics. There's going to be a whole other set of steps, but nonetheless, I think this particular mathematical feature of Schrodinger's equation and the fact that you're using complex fields would get a kind of physical cache value following this way of thinking about it, that I don't know of any way starting with I as the square root of -1, for example, that equally gives me a sense of, well, what's going on in nature that I'm using this thing.
Okay, just a quick follow-up. So the thing is, how we should think about the wave function is rather as there are two physically real fields and real with respect to existing.
Yes,
okay.
I would say that, yes. I mean, if
Okay.
if someone were to say, oh no, there's only one field, but one part of it controls the time evolution of the
Mhm.
other, and vice versa. Again, it seems like you've said the same thing again. I'm not,
Yes.
you know, I don't, counting one or two,
Mhm.
you know, I'm not sure what that amounts to as
Okay.
as a physical hypothesis.
Okay, great. Thank you.
Thanks. So let me read another question from the chat. By the way, there are also several comments, so you might later on still need some time to read it. So the question is by Francisco Bento. In pilot wave theory, oh, where's the chat now gone? Okay. There is a natural separation in two real functions, R and S, and two first order in time derivative equations appear. Would those equations for S and R be candidates for the RFD system? Where is Tim? Oh. Is he gone?
Did we lose him?
Well, I don't see him anymore.
Seems we did.
I will just give a call to Franjo where he is hosted just to check is everything okay.
Okay.
Maybe when
Thank you very much. So let's wait.
maybe he comes back.
So we get info. His battery is
No.
Batteries.
empty, but he will be back in a minute. Okay.
I just looked over and said, I'm almost out of power. And
And that was it.
I started with a full battery. I thought I'd be okay. And then, okay, anyway, I'm plugged in now, so that's fine.
Okay, we missed you already. So should I read the question again?
Yes.
Yeah.
Okay, so question by Francisco is, in pilot wave theory, there is a natural separation in two real functions R and S, and two first order in time derivative equations appear. Would those equations for S and R be candidates for the RFD system?
Yeah, I mean, candidates, obviously, and quite honestly, I haven't thought about, I mean, this is absolutely an obvious question to ask, and I haven't gotten far enough along in this to think it through, right? So you want to say, all right, I want to think about reciprocal first order, a pair of reciprocal first order equations. The obvious thing that occurred to Schrodinger was to take your complex field and think of it as a real field and an imaginary field, and then have each of those control the others. But as is pointed out quite correctly, well, maybe I could sort of separate it instead into amplitude and phase, right? That's again, I now have two degrees of freedom. Maybe I can now, how well is that going to work? I just think I would have to look at what the equations look like if I break it down that way, as opposed to if I break it down the first way. There's a great appeal. I can see a great appeal of trying to separate out the phase as somehow an independent degree of freedom, and then the amplitude as an independent degree of freedom. That doesn't give you the obvious way to get to this kind of structure, but whether if you do it that way, you might end up with something that looks different, but nonetheless has the same characteristics. And I'd be very interested to find out. But as I say, this is all starting at a very simple level of classical theory, giving you a model that does seem to be suggestive of features of quantum mechanics. The other issue is, of course, besides, do I break it down in terms of real and imaginary or amplitude and phase? If you bring in particles, if you want to do a pilot wave theory, then you have to look at the structure of the guidance equation, which I haven't, I didn't write it down or anything. The guidance equation also has an I in it, right? So it would suggest, at least one way to think of what it's suggesting is that you have two fields and one of them is doing the job of guiding the particles and the other one isn't doing that job. It's more or less doing the job of guiding the other field. But I haven't thought this stuff through, so I don't, I think there are a million questions people could have and ways of pursuing this idea, and I would like to pursue them all, but I haven't been able to do any of them properly enough to say anything about it.
Okay, thanks. So let's pass on to Aurélien.
Okay, can you hear me?
Yes.
Thank you very much. So nice for this great talk. I have a historical remark and also a question. So the historical remark, I think, is related to the origin of wave mechanics. In some sense, if you go back to Newton or people like Hamilton, there were already a lot of analogies with optics and mechanics. Newton already thought about that. There's a guidance theory, somehow like photons, or not really photons at that time, but the particle guided by a wave to explain the famous Newton rings, for example. And Hamilton also developed the famous Hamilton-Jacobi equation, which is fundamental for understanding Bohmian mechanics, for example. So there were already a lot of elements in the 19th century. But what you say about the Maxwell equation is very interesting, because this idea to combine the two fields and to define some kind of wave function for the photon has been also suggested by by de Broglie in the 20s and in the 60s, and it's also linked with the Dirac equation for these guys. So you are probably touching to a very important relation to between optics and electromagnetism and electrodynamics here, it seems, in your talk. And just this kind of remarks I wanted to do. Yes.
Yeah, I mean, look, I'm certainly aware of, I'm aware of the de Broglie double solution sort of idea. I don't know the details of it very well. And I'll just make a comment. Again, I appreciate everything you just said. I'll just make another comment. When I wrote down the Maxwell equations, I only did the dynamical equations, right? And there are these two other equations that I left out. One having to do with the divergence of B, and the other having to do with the divergence, what we call the divergence of B, the divergence of E. The divergence of B being 0, which we normally say, oh, that says there are no magnetic monopoles. On my way of thinking about this, and I'll just say this again, just to whet people's appetite for whenever I finally can publish this stuff. That turns out just to be a mathematical triviality. If you think that the B field itself is derivative, which is what you ought to think because of the Aharonov-Bohm effect, there's something like the A field, which is fundamental. I told you I have these two fundamental things that go lift and drop fields. So the A field is a 1 field. If you lift that, you get a 2 field. That's the B field. If you try to lift that again, which is what taking the derivative would correspond to, it's automatically 0 because the lift of the lift is 0. The drop of the drop is 0. That's like the boundary of a boundary is always 0, or the exterior derivative of an exterior derivative is always 0. So one of those equations turns out to be a mathematical triviality. And the other one is that the divergence of the electric field gives you the charge density. That one I want to treat as actually a definition. It's not, as it were, a physical law. It's just that charge density just is what corresponds to the divergence of the electric field. And it can be non-zero. And again, when you do this in a discrete setting, you get very interesting results. You can talk about the charge distribution of a so-called point particle. It has an interesting charge distribution. This is all also recent stuff. But there are a million ways you could go with this, right? I mean, it's not like you start on this and you're on some iron tracks that lead you to one way. And I can certainly see that a lot of the things that De Broglie was thinking about would be relevant to and similar to some of the things that are coming up here. Yeah.
Okay, thank you.
Thanks. Okay. So let us go on with Lorenzo Marcone. Lorenzo?
Hi, yeah, I just wanted to point out a couple of papers that might be of interest to you, because there is this paper by Ettore Majorana in which he does exactly, I don't know if it's exactly, but a very similar thing that you was pointing out, by taking the E field and summing I times B field. He calls it H, but anyway, it's a magnetic field. And then he derives a Schrödinger equation for that, or rather a Dirac equation. So maybe I tried to upload the PDF file on the chat, but it didn't let me. So I just put the
web address for it?
No, the web address. I can send it to you if you want. Yeah, anyway, that might be relevant to what you're doing. Another thing I wanted to point out is that I think in the quantum info community, people typically refer to the papers by Escher Perez and by Tony Assin and his group, which both of these papers claim that they have experimental proofs that you need complex numbers, because of course it's just part of the postulates of quantum mechanics. So it comes from some kind of experiments, and they point out, for example, the Tony Assin paper proves that in an entanglement swapping similar to a Bell scenario experiment, but with two Bell pairs, you cannot describe the statistics that comes out from a real quantum theory. You need complex quantum theory.
Yeah,
So that's what I think in the quantum info community is considered the proof, the experimental proof that you need complex numbers.
Yeah, so this sounds familiar. I was just speaking last week or so to Nicolas Gisin.
Yeah, exactly.
And I think he mentioned exactly the same thing.
Yeah,
right? Oh, there's an experimental proof you need imaginary numbers.
Yeah.
Now, from my point of view, I haven't read the papers, but because of the way I think about the mathematical representation of the physical state, to say you must use I strikes me as something I can't even understand from what premises one could get that, because other ways to achieve the same results without using that particular piece of arithmetic structure. But I certainly, this was news to me, and so you're the second person who mentioned it as something that might be relevant. Yeah.
Yeah, definitely. I think so. you might find it interesting. Anyway, I can send you the PDF of the Majorana.
Yes, I'd
Actually,
appreciate that. Thank you.
yeah, it wasn't published by Majorana, but it was published by other people combing through the Majorana notebooks. So the paper is by other people, but the idea is from Ettore Majorana.
Thank
Okay,
you.
cool. Thanks for the talk. Very nice.
Great. Let us go on. There is another question by Angel Garcia Chung. So Angel.
Hi, Tim. Thank you so much for your very interesting talk. I was wondering whether this complexification in the Hamiltonian mechanics is actually what you do in the standard QFT whenever you are trying to build the Fock space, for instance.
I don't know. I mean, I know how Fock spaces arise, but it never even occurred to me to ask the question you just asked, and my control of QFT is not strong enough for me to have any intelligent comment. So maybe I don't know. I wouldn't want to venture to say it.
Because I'm seeing somehow a connection whenever you introduce the annihilation and the creation operators are classical in classical, not in classical mechanics, but in complexified classical mechanics. And then once you define the one particle Hilbert space, you introduce a complex structure, so on and so forth.
I can see, yeah, I can see some of the mathematical analogies you're pointing at, but I don't understand them deeply enough to say anything intelligent about them.
Thank you.
So I mean, in the chat, there is still a lot of comments and also a lot of links to several papers. I'm not sure if you can still look at it later on. Anyway, there is another question by Siddhant. I don't know, Siddhant, you want to ask it to Tim? Or should I read it? Siddhant is not answering. So he asks if he's still there. Yeah. He asks about particles with spin. Is anyone wondering why R e to the is doesn't seem to be the starting point in pilot wave theory when dealing with spin? Also, the time reversal transformation for spinners is not a mere complex conjugation. It includes, in addition, a shuffling of the wave function components. So any thoughts on that?
Well, the thought is the one that Siddhant knows perfectly well, which is that I have not thought deeply enough about spin, and it wouldn't surprise me at all that everything I said, which is perfectly fine for Maxwell and perfectly fine for a scalar, you know, for a spin zero field, might go completely crazy for spin. And that's a wonderful question to ask. You know, again, I'm building by a slow set of steps. I got kind of close enough that I guess everybody can see standard quantum mechanics without spin that we first learn is within view. Spin is then another, you know, level of complexity. The fact that it falls somehow out of the Dirac equation is very interesting because the Dirac equation, again, is a first order equation. I don't understand this stuff well enough at this point to make comment. Of course, it would be quite interesting. I mean, it would also be an interesting result if time reversal just isn't implemented by complex conjugation once you get to spin. It would be another flag telling you, be careful. Real particles that we deal with have spin, but many of us have spent a long time thinking about the spin zero case and maybe are mistakenly believing that we understand things that once you add spin into it aren't true anymore. That would be, to me, a very interesting result. So I don't feel obligated for it to come out one way or the other. I think it's interesting whichever way it comes out, right? If it turns out that some simple analog to complex conjugation works, that's interesting. In a way, if it doesn't work, that's even more interesting, right? It's telling us that we need to think much more deeply about spin than I think many of us have, certainly than I have. So however it comes out, I'll be, happy.
Okay, Siddharth, thanks you very
Now
much.
I
You
can
can-
speak.
I know you can speak. Okay.
I just pointed out these for everybody to think about because our discussions just exclusively revolve around single spin zero particles. But when you read about spin and so on, a lot of things are so different, especially when you do the many body theory. The wave functions are just exponentially growing in the number of components. So yeah, just wanted to point this out and wanted to hear what you had to say.
Yeah.
Thanks.
So that might be exactly the place to see, gosh, this is really something new that we don't have any good classical analogs for at all. And we ought to be focusing on that. Yeah.
Mm. Thanks.
So there is one final question by Dirk. I think we should have it the final question now.
Is it the final? Yeah, I just wanted to add on what
Well, I'm not sure.
what Siddharth was saying. I think in general, one should look at the representation of the Poincare group in terms of, I mean, this vector spaces of solutions of wave functions, and I mean, all the particle zoo of the elementary particle physics or the standard model comes out basically as representations of the Poincare group. Yeah, so there's, I think, one question whether to think about why complex numbers, but I think there's maybe an even much more general path to say, well, more or less the whole standard model is the wave function, but with different representations of the Poincare group. So all the spinor representation, the projective representation, and so on and so forth. And I think there's a lot of structure in there as well. So I'm not sure if these questions, whether complex numbers are important or whether these representations are important, are leading along the same path. But I would say, adding on to Siddharth's comment, yeah, not just the spin half case, but I mean all the representations that we have of the Poincare group somehow need some explaining, or at least there's a nice fact that we can more or less predict the whole zoo of elementary particle physics by these nice symmetries. Yeah, so that.
Yeah, I mean, let me make a really controversial and you'll find extremely objectionable comment about that. My own view is that the violations of Bell's inequality have not been deeply enough appreciated, right? And if you say, which I think is correct, that tells you there's something like superluminal causation. You're not going to get away from it. Then you ask the next question, well, how do I implement that cleanly in my physics? And I guess everybody can agree with this. The easiest way to do it, I'm not saying the only way to do it, the easiest way to do it is to put in a preferred foliation. And if you put in a preferred foliation, then representations of the Poincare group or the Lorentz group are actually misleading because the fundamental physics doesn't respect those symmetries. What you need is an explanation for why the phenomena approximately at least respect those symmetries. And you would need to get that by some clean emergence out of a fundamentally non-Lorentz invariant theory. But here you've got a choice point, because if you're going to stick to the Poincare group as your fundamental thing, you're pretty much ruling that out. And I want to do the opposite. I want to rule it in. And so from that point of view, those symmetries are not fundamental. You need a good explanation for why they're emergent and why they're emergent to such good approximation as they are. And again, you know, it's a choice you can make. You can say, no, I'm so convinced of something like a relativistic theory of space-time structure that I just want to start with that as my fundamental principle. All I have to say is, as a historical matter, and nobody can deny this, relativity was devised in the first place to deal with Maxwellian electrodynamics, which is a local theory. And GR was devised to pretty much reproduce Newtonian gravitational theory, which is also a local theory, at least if we put a time delay in for the gravitational effects. And so those theories are local, so they don't need a preferred foliation. You can get away without it. But the violations of Bell's inequality, you know, those theories also cannot violate Bell's inequality at space-like separation. And I think that's the deeper point, right? That's a point we know. I think it's really deep, and I think it tells us, let's start with a structure where the violation of Bell we know how to deal with. And then hope to explain in the end why relativity worked as well as it did, just as quantum theory rejects Newton, right? Doesn't take Newtonian principles as fundamental, but of course is confronted with the emergence of classicality, right? You do need to explain why Newtonian mechanics worked as well as it did in the situations where it worked. Now, you know, this is a place where you're exploring the space of all possible theories, and everybody's going to have to take their little thread of what I think is a fundamental thing to hang on to guide me through this. I personally would not take the Poincare group for those reasons. Also, I'm dealing with discrete spacetimes, and you don't even have any continuous symmetries. So, you know, I'm very far away from your starting point. So each of us can go our own ways and see where we end up, right? Just be very self-aware of what you're doing and why you're doing it.
Well, I was not really attributing to locality in that sense, that I think you're using it like in terms of Bell's inequalities. I mean, I was rather referring to the fact that, I mean, the wave equations that are used in the standard model are basically all the wave function, twice time derivative is equal twice space derivative, basically. And then the add-on to get to different families of particles is basically looking for finding representations of the Poincare group on this vector space of solutions of the wave equations. And I think there, I mean, I mean, of course, the first question is, why real or complex? But the next question would be then, why a C2 or a C4 spinner, or why different? So I'm not referring to non-locality. I mean, I think that has rather is rather situated in the fact that we have a wave function configuration space and not on space-time. Yeah, but I think the fact that the standard model, in the way it works so well with wave equations that respect the Poincare symmetries. I mean, at least a lot of success came out of that story. And I think even though there might be a much deeper theory that in the end says, look, it's only emerging because of this and that, I think that would be okay. But nevertheless, I think we would still have to explain a little bit why. I mean, all the elementary particle families that we know somehow fall out as representations of the Poincare group. At least it's something that one can't deny is an interesting mathematical fact. And I think the question that you ask about the eye could then ask about all these different representations as well. Why is that the most intuitive thing to do?
Yeah, I mean, there are lots of interesting. I'll just add one more. I was just talking to some people about, you know, we have this fact we all know, which is that the fundamental particles come in these three families. And Dirac had the idea that it had something to do with the three-dimensionality of space, but he could never work it out. I think I might have an idea about that, but you know, that's also something you can't deny it. It's there. Does anybody have a good explanation for why, in addition to the electron, there's the muon, and in addition to that, there's the tau, right? And similarly, right? Obviously, the observation that there are three dimensions of space, and then I mean, unless you're a string theorist, 3 dimensions of space and 3 generations, you might think maybe there's something to that, but that's just a guess, right? So there are lots of different clues, things that might be clues. I mean, this really is a mystery story, and you're not sure what's a red herring and what's a clue. Lots of different paths to follow out. I myself am making a bunch of bets just on stuff I'm interested in, and we'll see how all that comes out.
Yeah, thank you.
I think these were quite nice final words. Or did I miss any question from the chat? So if anybody wants to ask a question, please still you can raise your hand. I didn't keep up with everything, I guess, but I hope I read out everything.
Yeah, I quickly scrolled through. I think, Tim, in what you might be interested, or maybe you know the work already. So Detlef Buchholz is here in the chat. Unfortunately, he wrote me earlier that he can't use the microphone. And so he only wrote in the chat. I don't know, from the comments, it seems to me it would probably be interesting if you both get in touch. As also Detlef Buchholz has some theories and some works published on the nature of I. So I would say let's maybe leave it to that, because I think you two will probably.
Yeah, I don't know whether I'll be able to access the chat after this. So if anybody has something you think I ought to see, just email it to me to make sure that I get it.
Unfortunately not. So Detlef Buchholz, I can, if you hear me, I can also put you two guys, of course, in contact, or you write each other directly.
Yeah.
Okay. All right. But I think we was a lively discussion. Thank you for hosting us, Paula. So we have not too many upcoming talks now on the list. There will be upcoming talks, of course, but we'll use a couple of the slots here. Whenever there's no talk, we usually have something like a thesis defense or like a local talk here, which we do in the same time slot as usually. So the next talks we'll announce again on the newsletter. Yeah, thanks so much, Tim. It was really a great discussion. And thanks to everyone for joining. I'll keep you posted.
That was helpful. Thank you.
Thank you very much. I'll keep you posted on the newsletter. And yeah, hope to have lively discussions in the near future. So stay safe and see you all soon. Bye-bye.
See you.